In this class we are going to discuss about the refraction at a single spherical surface. Consider a single spherical surface, it's made up of glass. On this side it's centrally made up of glass, on this side it's centrally made up of air. Okay. The question is about if I place the objects on this side on the principal axis of this glass sphere, right, at what location the image of this object will be produced. It's what we have to calculate. How can we get that? So let's say that this glass surface is having some radius of curvature. If I imaginarily extend the means, I can able to construct a sphere. That sphere is said to that any sphere will be having some center. It's a center of curvature and it's a radius of curvature. Okay, we know all these things. Now the question is we have to calculate the position of the image of these objects. Okay, how can we get that? To get it, we can use the laws of refraction which we discussed in the previous class. From the object we can imagine the two light ray. So this, let me assume this light ray is approaching our glass surface in this way. At this point of incident, if I draw the normal line itself is going to be looks like this. So here the angle of incident is 0, so angle of refraction is also 0. So this light ray will goes undeviated. From the same object I can consider one more light ray also, but this light ray is approaching our glass surface at some certain angle. So at this point of incidence, if I want to get the normal direction, what I will do is I will join that point to the center of the curvature, and if I imaginarily extend that line, I will be getting the normal line at that point. So here the incident ray is making some angle, I angle, okay, so to the normal line. So since the light rays are entering from air to the glass, it's going to bend toward the normal. So it's going to bend toward the normal. So these two refracted light rays, okay, is meeting at this point. So that's where the images of these objects will be produced. So if O is the object portion, I is going to be the image of this object, okay, and we can make one more assumption here. See, what is the idea we are discussing? It is strictly applicable to the paraxial rays. So obviously this point of incident, if you wish, we can name them as A. Okay, this point of incidence is going to it's going to be located very closer to the P. So we can, for the time being, we can ignore the curvy nature of the surface. We can treat them as a straight line. Okay, so we can call this point as a M. For paraxial rays, the AP is approximately equal to the AM. Okay, so that assumption is reasonable assumption. So for paraxial rays, automatically the I value is also going to be very smaller. Yes, since the A is located very closer to the P, so obviously I value should be very smaller. When the I value is smaller, then obviously the R value is also going to be very smaller. So I and R values are very smaller for paraxial rays, I and R, and let me call this angle as a alpha. Okay, this angle is a beta, this angle is a gamma. If I and R values are so smaller, then alpha value will also be smaller because this A is located very closer to the P, so automatically the alpha is going to be very smaller then. So once if I, R, alpha values are fixed, then automatically gamma value, beta value will also be very smaller. Okay, now we can try to establish the mathematical relationship between these various angles. Okay, okay, consider AOC triangle. Okay, consider AOC triangle. From the AOC triangle, you can clearly infer the interior angles are alpha and gamma. So it's a property of the triangle. So if you sum up the two interior angle, the two interior angle is going to be equal to the third exterior angle, so which is equal to the I. So these two interior angles are exactly equal to the third exterior angle, so which is equal to I. Okay. Similarly, if you consider this ABC triangle, will be calling this point as a B. So let me consider the ABC triangle now. So there also you can apply the same principle. Here the interior angles are R and beta, exterior angles are gamma. So I can write the sum of the two interior angle R plus beta equal to gamma. So out of this I can able to write R equal to gamma minus beta. So now I got the incident angle, I got the reflected angle. So we know the way to correlate them, because Snell's law dictates the relationship between them. So since it's an air medium, it's a glass medium, I can able to make use of the Snell's law to get the relationship between the I and R. Okay. So sine of I by sine of R, which is equal to N2 by N1. So N2 is nothing but glass medium, N1 is nothing but air medium. So for smaller angle, the sine of theta can be replaced with theta itself. So sin I and sin R can be replaced with I by R itself. For smaller angle, we can make use of this approximation. So NA into I equal to NG into R. So in the place of I can replace this. In the place of R, I can replace this. If I do that, I will be having like alpha plus gamma equal to Ng into gamma minus beta. I got expression like this. Okay. And since alpha value, beta value, gamma value, I value, R values are so smaller, so sine of alpha can be approximately written as alpha itself or tan alpha itself. Similarly, sine of beta and sine of gamma can be replaced with tan of alpha or alpha itself. So something like that. Similarly, I can, since all the angles are smaller, I can make use of the smaller angle approximation for all angles. So a sine of beta is approximately equal to the beta itself or equal to the tan beta. Similarly, sine of gamma is approximately equal to the gamma itself or equal to the tan gamma. Now consider this part of the triangle. Okay. From this triangle, I can say that sine of alpha equal to tan of alpha equal to AM by OP. Okay, since the A is lying very closer to the P, this distance is negligible. So AM or OM can be replaced with OP itself in that case. Similarly, tan of beta, okay, it's a beta angle, right? So tan of beta can be replaced. Consider this triangle, this part of the triangle. The tan of beta equal to opposite side is AM, adjacent side is PI. Similarly, tan of gamma equal to, consider this part of the triangle now. Tan of gamma equal to opposite side is AM, adjacent side is PC. So replace all those angle over there. Okay. So it's approximately equal to beta, it's approximately equal to gamma, it is equal to alpha itself. So in the place of alpha and beta and gamma, we can replace those quantities. If I do that, I'll be getting this. N of A, alpha can be replaced with AM by OP and gamma can be replaced with AM by CP. And gamma can be replaced with AM by CP, beta can be replaced with AM by IP. Now try to simplify this. Just multiply the NA into the terms and take the AM as a common factor and cancel off them. So we will be getting a NA by OP plus NA by CP equal to NG by CP minus NG by IP. Okay. So bring the IP parameter to that side, so to this side, so I will be having like a NA by OP plus NG by IP equal to NG by CP minus NA by CP. Okay, so I got a expression like this. So far the OP, IP, CPs are merely distances, but here I am going to introduce the sign conventions. OP is nothing but, so here we place the objects. So from the object towards the refracting surface, the light rays are going to approach or propagate in this direction. So it is the incident ray direction. So along the direction, if I measure any horizontal distances from the poles, it should be a positive. If I measure any horizontal distance in oppositions to the incident ray, it should be negative. So OP is nothing but it's the object distance. So object distance OP should be equal to minus of u. Similarly, PC is nothing but it's the radius of curvature. So we can replace it with plus r. Similarly, Pi is nothing but image position. So we can call it as a plus V. So in the place of OP and PC and Pi, we can replace these quantities. So I'll be having like NA, OP can be replaced with minus of U, and NG, IP can be replaced with V. So if I take the 1 by Cp as a common factor, I will be getting this. So Cp can be replaced with R. So if I rearrange this equation, I will be getting a Ng by V minus Na by U equal to Ng minus Na by R. So I got an equation like this. So this equation is so important and so vital one, because we will be using this equation more often to work out the NEET level questions or JEE level questions. So if you are having a single spherical surface, and if you know where you place the object, if you know the object distance, and you can able to get the image distance once if you know the radius of curvature of the spherical surface by using this formula. Okay, here Ng is glass medium, Na is air medium, and Ng minus Na. Generally I can rewrite the same equation into this form also. Ng is nothing but second medium, right? So N2 by V minus N1 by U equal to N2 minus N1 by R. So it's a more general form. Suppose if that spherical refracting surface is made up of water or any other medium, then we can generally use this formula then. So once if you got this formula, right, by using this formula twice the time, we can able to get the Lensmaker equation. I will derive the Lensmaker equation also now. Consider a convex lens now. Consider a convex lens now. You know that convex lens surface is made up of two spheres, because if you imaginally extend this surface, let me call this surface as a 1 and this surface is a surface 2. Okay, if you imaginally extend this surface 1, it could form a sphere with the center over here. Okay. Similarly, if you extend this curvature imaginarily, it could also form a sphere, and that sphere can also have some center. Okay. So obviously this convex lens or concave lens, we can able to create the shape of the surfaces by using the two imaginary spheres, imaginary glass spheres. So with that assumptions, right, I am going to derive the Lensmaker equation. Imagine here we can consider a convex lens. I placed the object over here. Okay. Consider the this part of the surface alone. Consider surface 1 alone. We are going to study the refraction of this single surface alone. Okay, if this entire side is made up of this material, right, this glass material, obviously we know where the image will form. We have derived the formula for that, right? So this is where the image will be formed. We can call the image portion as a I dash. So object distance is U, image distance is I, it's a minus u technically, okay. Okay, so if I ignore the presence of this surface, okay, if I consider only this surface alone, then obviously because of the refraction at this single interface, the image of this object might be formed at this position. So we can able to calculate the positional distance by using the end results of this derivation. So n2 by v, so on this side it's entirely made up of glass, we can make that assumption, okay. So the n2 is nothing but glass medium, n2 by v, so here the v is nothing but v dash, because it's not a final image portion. I will tell you the reason for it, okay. Let me call this p I dash as a v dash, v dash is nothing but p I dash, okay. n2 by v minus n1 is air medium, so n1 by u equal to n2 minus n1 by r1. So generally, see, we are studying about the interactions of this surface alone. So the radius of this surface is measured in this direction only, because the center of the surface is going to be lying on this side only. So r is positive then, as per our sign convention, okay. Everything is fine. Now imagine, but we didn't have only this surface alone, we have the presence of this surface also. So to study the effect of this surface and its presence, what we can do is, see, consider the presence of this surface now. So this image is going to serve as a virtual object to this surface. So there is a difference between the real object and the virtual objects. In the case of real objects, the light rays from the real objects has the tendency to diverge out, but in the case of virtual objects, the light rays has the tendency to converge in. So this I dash is going to serve as a virtual object to this surface. So as far as this surface is concerned, so our object is presenting on this place only. So because towards that objects only the light rays are converging in, right? So okay, if you consider this surface and if you apply the same derivation end results, okay, for that surface, you will be getting these results then, because this time we can assume the entire side is made up of glass, right? Based on the assumption only we got this image portion, right? So as per that assumption, our object is lying on the glass medium. So virtual object is lying on the glass medium, but the final results are going to formed on the air medium. It's the final image. So object is in the glass, image is in the air. So if you rewrite the same equation one more time, you will be getting like n2 is n air, n2 by v minus n1 is glass medium. So here the pi dash is going to serve as a object distance. So I can say that it's a v dash. So which is equal to n2 minus n1, which is n air minus n glass by r2. So I make use of this end results twice the times to these surfaces. Okay, if you consider this equation as a 1 and this as a equation 2, if you sum these two, you will be getting the Lensmaker equation then. So just add this, you will be getting like this parameter will get cancelled off. So I will be getting like n of air 1 by v minus 1 by u equal to, here I can take ng minus nr as a common factor. So I will be having a 1 by r1 here, but here we have a nr minus ng, but I have taken the ng minus nr as a common factor. So I should put a minus of 1 by r2 over here. So I got a results like this. Now I can simplify this even more. I can bring this n of r to the side, so I will be having like a ng minus nr by nr into 1 by r1 minus 1 by r2. On simplifying this, I will be having like a 1 by v minus 1 by u equal to ng by nr minus 1 into 1 by r1 minus 1 by r2. So, and here comes the final step. So, I can say that for a lens, it would be convex lens or concave lens, that does not matter. If the object is located at the infinity, the image is going to be formed at what? When the u equal to minus of infinity, v equal to f. Is it right? So, we can make use of the substitution here. When the u is equal to the infinity, v is equal to the f. If I substitute that, I will be having like 1 by f minus of 1 by infinite is 0, so we do not have to consider that. So, 1 by f equal to ng by nr minus of 1 into 1 by r1 minus 1 by r2. So, here we got the Lensmaker equation. This equation is called as Lensmaker equation because the lens makers, all the lens makers in the markets are going to use this equation to construct a lens. So, if you want a lens with a particular focal length, so you have to focus on the curving the surfaces, because if given the two pair of surfaces are having the given radiuses, then obviously its focal length is automatically fixed accordingly. So, that is why this equation is called as Lensmaker equation. And here we have a one remarkable conclusions, that is, if the entire lens setup, if the convex lens setup is placed on some medium instead of a air, imagine it is a convex lens, but this convex lens is placed on some medium, it is not air medium, it could be some other medium, it could be a water, it could be a diamond, or it could be anything. Okay. So, if I place this convex lens in some other medium, okay, so then the refractive index of the medium is n1, the refractive index of the medium 2 is n2. Okay. So, then for a more general case, we can use this formula 1 by f equal to ng can be replaced with n2, nr is replaced with n1. So, it is a more general form of the Lensmaker equation. It could be applicable for any medium. So, from this equation itself we can understand one thing. If the refractive index of the glass medium, if the refractive index of the material out of which the lenses are made is having more refractive index than the surrounding medium, then the convex lens is going to behave like a converging lens, but the case is reversed. If the surrounding medium, okay, is having more refractive index than the material out of which we made the lens, then the convex lens is going to behave like a concave. The nature of the lens will subject to the change. So, you cannot blindly tell the convex lens will always having the converging nature and concave lens will always having the diverging nature. It need not be the case all the time. So, the nature of the lens strongly depends on the medium in which we place the lens. If the surrounding medium is having a lesser refractive index than the refractive index of the lens, then that lens is going to behave like a converging lens or diverging lens. Okay. But if the medium is having more refractive index, okay, comparatively speaking with the lens, then the convex lens is going to behave like a diverging lens and the concave lens is going to behave like a converging lens. Okay. And we can just note down this formula. Okay, we will be using this formula more often. So, by using this formula we can understand the various other cases as well. For example, in market we have the different kind of lenses. We have a biconvex lens, plano-convex lens, plano-concave lens. So we have the different kind of lenses in the market. So we can try to get the focal length formula for all kind of lenses by using the same ideas now. Okay. For example, if you consider a double convex lens, we will be having the two surfaces and its refractive index is N2. The surrounding air, the surrounding medium is having the refractive index of N1. Okay, let us say that this surface is surface 1, its radius is R1, and this surface is having a radius of R2. I told you that if you place the objects on this side, okay, any horizontal distance measured from the optical center in the direction of incident ray, it should be treated as positive. Any horizontal distance measured in opposite sense to the incident ray, it should be treated as negative. So as per our sign conventions, R1 is positive whereas R2 is negative. Okay, negative. So if you use this formula, then what I will be having is one by f equal to n2 by n1 minus 1 into 1 by r1, r1 is positive, minus of minus r2. So you will be getting what? Plus. So obviously what you got? N2 by N1 minus 1 into 1 by R1 plus 1 by R2. I have applied the sign conventions here. So while you are using this Lensmaker equation, you can substitute the R1 value or R2 value with proper sign conventions. Okay. So for double convex lens, the focal length, since the whole quantity is going to be a greater than 1 or it's going to be a positive, so that tells you that the convex lens is going to have the positive focal length. But for double concave lens, the case is opposite. If you consider double concave lens, its refractive index is N2, it's placed in the medium of N1. So it's surface 1, it's surface 2. This surface 1 is having the center on this side, so its radius is negative, whereas this surface is having the radius at center on this side, so its radius is positive. So again, if you use the same formula, right, if you use the same end results, what value you will be having for double concave lens? 1 by f equal to n2 by n1 minus 1 into 1 by r1, so r1 is minus of r1 minus of 1 by r2, r2 is positive. So the whole quantity itself is coming in negative. That tells you that the focal length of the double concave lens is negative. Okay, and there is a special case also. For example, we may have a equiconvex lens or equiconcave lens. We may have equiconvex lens. So which means we will be having a double convex lens, but both of the surfaces are having the same radius. The value of this radius is identical. So, but again, as per our proper sign convention, right, this radius is positive, so R1 is positive, R2 is negative. Yes, it is measured in this way. So if you use this formula, you will be getting like 1 by f equal to n2 by n1 minus 1, 1 by r1 minus 1 by r2. So what I got is n2 by n1 minus 1, 2 by r. It's a formula we have for equiconvex lens. Similarly, we can derive the similar kind of formula for equiconcave lens also. Similarly, for equiconcave lens also, so the value of this radius is identical to this radius, but the only difference is, since this surface is having the center on this side, so its radius is measured in this way, it should be negative. So but this surface is having the center on this side, so its radius is measured in this way along the as per our sign convention, this radius is positive. So if you use this R1 and R2 in that Lensmaker equation, we will be having like 1 by F equal to N2 by N1 minus 1, 1 by R1, it's a minus of R, minus of 1 by R2. So R2 is positive, but even then in front of that R2 itself we have the negative. So the total whole quantity itself is coming in negative. So I will be getting N2 by N1 minus 1 minus 2 by R, so which is equal to 1 by F. So this is the formula we have for equiconcave lens. Suppose if you got the plano-concave lens or plano-convex lens, the cases are different entirely. I will tell you that case also. Suppose if you are having a plano-convex lens, imagine it's a plano-convex lens. So it's a double convex, but it's a plano-convex. I hope that you can able to understand the differences very clearly, because this lens is its appearance is resembling the convex lens, except the fact that the one surface of the convex lens is appearing to be a flat. So that's why this lens is called as plano-convex lens, and its focal length also can be calculated by using the same Lensmaker formula. We know that it's a Lensmaker formula, 1 by F equal to N2 by N1 minus 1, 1 by R1 minus 1 by R2, but here R1 is positive, okay, it will be considered R1 value is equal to R, but whereas this surface is flat, so we can imagine this surface, since it's literally flat, okay, we can imagine its radius of curvature is going to be infinite, because infinitely large sphere may appears to be flat at a local points. For example, Earth is having a very large radius, so that's why locally it appears as a flat. So the same assumption you can make. So here R2 is going to be a infinite. So then 1 by F equal to N2 by N1 minus 1, 1 by R minus 1 by infinite. 1 by infinite is 0. So I got a expression like this. So it should be a formula for plano-convex lens. Similarly, you can derive the formula for plano-concave lens also. Suppose if you are having a plano-concave lens like this. Okay. Again, imagine here the R1 is negative, whereas R2 is infinite. So 1 by F equal to N2 by N1 minus 1, 1 by R1, R1 is minus of R, R2 is infinite. So I got a N2 by N1 minus 1 into minus of 1 by R, which is equal to 1 by F. So it's a formula we have for plano-concave lens. Okay. Apart from that, we may have concavo-convex lens and convexo-concave lens. So for whatever would be the shape of the lens, you have to use the proper sign conventions to get the focal length. See, from these results you can clearly understand one more remarkable fact. What is that? So generally 1 by V minus 1 by U is literally equal to what? 1 by F. So we derived the formula for thin lens. So 1 by V minus 1 by U equal to 1 by F. This formula is called as lens equation. and this equation also should be used with proper sign conventions. If you try to substitute the u values, v values, you should substitute with the proper sign conventions. If you are blindly substituting the u values and v values, means it gives you the wrong results. So this lens equation can be used to find the position of the images formed by the convex lens or concave lens. Again, before discussing about the uses of this lens equations, we should develop some ideas related to the image formed by the convex lens and the concave lens. So there are certain rules. By using those rules, we can able to locate the position of the image easily. I will tell you the rules one by one. Okay, so if I send any light ray parallel to the principal axis, after getting refracted, the light ray will pass through the focal point. It's the rule 1. Rule 2 is so obviously concave lens or convex lens, it will be having the 2 focal point and 2 center of curvature also. Okay, so if I send any light ray in such a way that if its path is directed if its path is directed towards the optical center, it goes undeviated. It's a rule 2. And rule 3 is if I send the light ray in such a way that if the path of the light ray is directed towards the focal point, after getting refracted, the refracted light ray will become parallel to the principal axis. It's exactly the inverse of the rule 1. It's a rule 3. Okay, and the fourth rule is principle of reversibility. So with all these rules, we can able to construct the image locations easily. I have drawn these rules to convex lens, and of course I can define the same rules to the concave lens as well. But here the rules are a little different. See, consider rule 1 here. If I send the light ray parallel to the principal axis, after getting refracted, it will start to diverge away, and if I marginally extend this light ray's path backwards, it appears to be coming from the focal point. It's a rule 1. Rule 2 is if any light ray is directed towards the pole, its path will not change, it will simply go unchanged. It's a rule 2. And rule 3 is it's exactly the inverse of the rule 1. So if any light ray is directed towards the focal point after getting refracted, okay, it will become parallel to the principal axis. So these are the rules we have. With this handful of rules, we can able to get the image formation theorem very easily for the various cases. Now we can consider the image formation diagram of a convex lens. Consider it's a convex lens. So it's a focal point, it's a center of curvature. I simply call them F, F, C, C. If you wish, you can call them as F1, F2, C1, C2. That doesn't matter. Okay. If any object is placed at the very far away from the convex lens, from the object, so whatever the light ray is coming, it may appears to be parallel to the convex lens. Okay, it may appears to be parallel to the principal axis because those light rays are seems to be parallel, because those light rays are emerging out from the object which are located very distant away from the convex lens. So these two parallel light rays, after getting refracted, it will simply pass through the focal point. So that's where the images of these objects will be produced. So if the object is located at the infinity, its image is going to be formed exactly at the focal point. In fact, you might have used the convex lens in your childhood, where you will be using the convex lens to see to burn the papers or to burn the sticks. You will be using it, right? So which means you will be focusing the light ray to a particular point. So which means that particular point is nothing but it's a focal point. So that distance between the lens and that point is called as focal length actually. Yes, the sun is located at very distance away from the convex lens, so apparently we can assume the light rays are parallel to each other. So when these parallel light rays are falling on the convex lens, after getting refracted, it will get converged to a point. That point is called as focal point. So exactly that's where we will be having the maximum intensity of the radiation. So if you put the paper over that, it can easily get burned. Similarly, for other cases also we can see, consider the same convex lens. If the objects are placed beyond C but at some finer distance, its image can be the locations of the image can be figured out through this idea. From the top tip of the objects, you can consider one light ray in such a way that it is parallel to the principal axis. After getting refracted, the refracted light ray will pass to the focal point. Okay. From the same top tip of the object, you can consider one more light ray also, but this time it is directed towards the optical center. So after getting refracted, it will goes undeviated. So both of these light ray will be meeting here. So that's where the image will be formed. Okay. If the object is placed beyond C condition, the image will be formed between the C and F. Image at object at. Okay. Similarly, if you place object exactly at the C, if you place object exactly at the C, the image will also be exactly formed at the C. I will tell you the reason for it. Yes, from the top tip of the object, you can consider two light rays. One light ray is approaching our convex lens parallel to the principal axis. After getting refracted, it will pass through the focal point. I can consider one more light ray also, but this light ray is approaching our convex lens in this way. So it tries to pass through the optical center, so its path will not get changed, it will simply goes undeviated. These two light rays are meeting at this point, so that's why we are having the center of curvature also. So obviously, if you place the object exactly at the C, the image will also be formed at the C, and the object size and image size are identical exactly for this case alone. All these images are real images, because if you place a paper over here, you can able to hold those images over there. So that's why these images are called as real and inverted image. Here the image is having the same size as that of object, but here the image is having somewhat shrinked image we got. Now consider another case. If the object is placed between the C and F, then its final image location can be calculated by using the same ideas. I am not giving you much explanation on this because you are already familiar with this now, right? I apply the rule 1, I apply the rule 3, so rule 2, both of these light rays are meeting B and C. So that's where the final image will be produced. So I can say that if the object is placed between the C and F, the image will be formed B and C, and the nature of the image is real, inverted and magnified image we can get. If the object is placed exactly at the focal point, the final image will be formed at the infinity on the other side, because these two light rays, after getting refracted, these two refracted light rays are appearing to be parallel to each other. So from high school mathematics we already know that if the two light rays are parallel, they will never meet, right? So but we can assume they may appear to be meeting at the infinity. So that's why the final image will also be formed. So if the object is placed at the focal point, the image will be formed at the infinity. So the formed image is real, inverted, it's extremely magnified. For convex lens, if the object is placed between the F and O, then cases are different. From the top tip you can imagine the two light ray. One light ray after getting refracted, it will pass through the focal point, and another light ray, if it's directed toward the optical center, it goes undeviated. So if you look into these two light rays, so these two light rays appearing to be diverging, right? So if these light rays are having the diverging nature, they will never meet even at the infinity. So if we imaginarily extend their path, this two light ray may appears to be coming from the same common point. So that's where the final image will be produced. So to this outside observer, right, to this observer on this side, these two light rays appearing to be coming from this common point. So that's where image will be produced. So as far as this external observer is concerned, the formed image is lying inside of the convex lens. So a convex lens can produce virtual image only for this condition alone. So when the object is placed between the focal point and the optical center, it can produce the virtual image. So exactly we will use this idea to understand the working of simple microscope. Okay, we will come to understand this later. So this is the lens equation, right? 1 by V minus 1 by U equal to 1 by F. Out of this equation, right, you can able to get the magnification relationship also. We know that magnification of the lens is nothing but, generally magnification means by that word we are comparing the size of the image with the size of the object. So magnification is equal to height of the image by height of the object. Height of the image is negative, height of the object is positive, whereas V is positive and U is negative. So this minus minus will get cancelled off. So we got a Hi by HO which is equal to V by U. So this is the formula I have for magnification. Whereas for mirror it's somewhat different, right? For mirror Hi by HO equal to minus of V by U. But for lens magnification is equal to Hi by HO equal to V by U. It's the expression we got for magnification. So we can modify these expressions into this following form then. Multiply the whole equation with U on either side. So we will be getting a U by V minus 1 U by F. So U by V is nothing but 1 by M minus 1 U by F. So 1 by M equal to U by F plus 1. I got a U plus F by F. So M equal to F by F plus U. This is the formula we have for magnification. in terms of object distance. Similarly, if you multiply the whole equations with v on either side, you will be getting like a v by v minus v by u equal to v by f. So you got what? V by u is nothing but m. So v by f. So 1 minus v by f equal to m. So 1 f minus v by f equal to m. This is the magnifications in terms of the image distance. So these are some important formula that is related to the lens, okay. And we can see, we can discuss one more image formation theorem also. See, we discussed the image formation theorems of the convex lens, but we have not discussed the image formation theorem of a concave lens. We will discuss that idea also now. Imagine we have a concave lens now, okay. Imagine I placed the object at infinity. So from the objects, whatever the light rays are coming, they should be parallel to each other. After getting refracted, those light rays will diverge away. So if we imagine extend this light rays path backwards, they appearing to be meeting at this point. So that's where the images of these objects will be produced. So if the object is placed at the infinity, the image will be formed at the focal point on the same side, okay. But the cases are different if you are placing the object at any finite distance means. Imagine if I place the object at any finite distance, okay, I can imagine one light ray from the top tip of the objects in such a way that it is parallel to the principal axis. After getting refracted, it will go like this. I can imagine one more light ray also. This light ray is directed towards the optical center, so its path will remain same. These two light rays is appearing to be meeting on this side if I imagine extend them backward means. So that's where the images will be formed. So the concave lens will always produce erect and virtual image all the time, okay. Now we can see the combinations of the lenses also. See, I have the two lenses in contact, okay. I have the two lenses in contact. Now my task is I should find out the combined effect of these two lenses. How can I get that? Let us say that this lens is having the focal length of f1, it is having the focal length of f2. I placed the object over here, so at u distance away from the first lens. So if only this lens alone is present means, and the image of this object will be formed over here. Let us say that, let me call the distance is I dash, okay, this distance is a v dash. So I can make use of the lens equation then. Now I have completely ignored the presence of the second lens. I consider only the first lens and its effect alone. So if I make use of the lens equation, I will be having like a 1 by v dash minus 1 by u equal to 1 by f1. Is it right? Now I can consider the presence of the second lens alone, but as far as the second lens alone is concerned, okay, this I dash is going to serve as a virtual object. It is going to serve as a virtual object. So the final image, let us say that. So for the second lens, okay, the I dash is going to serve as a virtual object. So it's where the final image is going to be formed. It's an object, it's an image, final image. For second lens, it's an object, it's an image. So final image distance is called as v, object distance is called as v dash. So I can make use of the lens equation one more time. 1 by v minus 1 by u, u is nothing but it's a v dash, which is equal to 1 by f2. Now add these two equations, equation 1 and equation 2, you'll be getting like what? 1 by v dash will get cancelled. So you'll be getting 1 by v minus 1 by u equal to 1 by f1 plus 1 by f2. So you got an equation like this, okay. So by using the two convex lenses, okay, we finally formed the image at this position, right. to form the same to form the image at exactly the same position, right, what equivalent focal length a single lens should have, we can calculate that. So see, we can replace these two individual lenses with a single lens, but that single lens is going to have the same effect as that of these two. So its focal length is f equivalent, we can assume like that. So for this lens, object is placed at the same u distance away, the final image is formed at the same v distance away. So I can make use of the lens equation 1 by v minus 1 by u equal to 1 by f equivalent. If you compare this equation 3 and 4, the right hand sides of the left hand sides of the equations are identical. So obviously right hand side also should be identical. So I can say that then 1 by f equivalent equal to 1 by f1 plus 1 by f2. It's the formula we got. Okay, when the lenses are placed in adjacent manner side by side, the equivalent focal length can be calculated by using this formula. Similarly, see, one more important parameter I just have to define now. So it's nothing but power of lens. Power of a lens is nothing but its ability of the lens to converge or diverge the light ray. So that ability is measured in terms of the power. Okay, the power of the lens is inversely proportional to the focal length, because if a given lens is having the ability to focus the light ray at very shorter distance, and it is said to be having more focal length, more power, because just imagine it's a convex lens. Okay, I am sending the parallel beams of lights on it. So after getting refracted, these light rays are converged at this point. Okay, now imagine another lens also, but this lens can able to converge the same parallel beams at shorter distance. So its focal length is less. So it is having more ability to converge light ray at shorter distance. So that tells you that this lens is should be having more power. Its power is more because it is having the ability to more ability to converge light ray. Its power is less. So the power and focal lengths are inversely related. So we got the formula then. So we can replace this focal length formulas in terms of the power also. So P equivalent equal to P1 plus P2. Simply, it's the formula we have. Okay. Similarly, if there is any gap between the lenses, okay, the two lenses are separated by a certain separation gap, then obviously we cannot make use of this formula, because these formulas are strictly applicable only when the lenses are in direct contact. But if there is any small gap, okay, if the separation gap between the lenses are d, then the equivalent focal length can be figured out, can be derived in the following way. Imagine this point is O1, this point is O2. Okay, I'm going to place the object over here. So let me imagine the height of the object is h1. From the top tip of the objects, one light ray is coming in such a way that it is parallel to the principal axis. After getting refracted, its path got changed. Okay, originally the light ray should have gone like this. Okay, but because of the presence of the first lens, its path got deviated. Okay, if there was no second lens, this light ray might have traveled in this path. Okay, but we have a one more lens also, so the path of the light ray is going to be deviated one more time. Okay, so you know that because of the presence of the first lens alone, these parallel lights are converged at this point. So this distance should be what? It should be f1. Okay. Similarly, see, the separation gap between the two lenses are somewhat smaller. We can make that assumption. In that case, this lens also, these light rays are also can be treated as parallel to the principal axis approximately. So after this, after passing through the lens too, this parallel light ray will also get converged to the focal point f2. It will get converged to that focal point f2. Let me consider these angles as alpha. If it's alpha, this should be alpha also. Okay. Similarly, we can consider this angle as a beta. If this angle is beta, and this angle can also be assumed as a beta, I told you very clearly, because here the degree of convergence are very small near to the lens, so we can assume these light rays are still parallel to the principal axis at this location. Okay. Now we can make use of this idea then. If you extend this line backwards, it will form some angle. Let me call that angle is here deviation angle. Because it's a incident light direction, it's a finally emerging out light direction. The angle between them two is called as deviation angle. Is it right? So I can tell that if this angle is beta, this angle is also beta. Is it right? Because alternate angles are equal. So imagine, consider this triangle. The interior angles of the triangles are alpha and beta. The sum of these two should be equal to the third exterior angle. Okay, I can write alpha or tan alpha are identical because the angles are so small. The tan alpha is equal to the alpha itself. So alpha or tan alpha equal to what? Consider this triangle. Tan alpha is equal to, what's the opposite side? Opposite side is H1. What's the adjacent side? Adjacent side is H1 by O1 F1. It's F1, right? O1 F1. So it's nothing but H1 by F1. Similarly, if you consider this triangle, this part of the triangle, okay, if we call this height as a H2, so if you consider this triangle, you can see very clearly tan beta is equal to, opposite side is H2, adjacent side is O2 F2, which is nothing but F2 itself. So H2 by F2. So tan beta is approximately equal to the beta itself. Yes, for smaller angle approximation, this assumption is valid. So if I sum this alpha and beta, I'll be having like H1 by F1 plus H2 by F2 equal to deviation angle. Okay. So to produce the same deviation angle, right, what equivalent focal length we need? Let me call the equivalent focal length as F equivalent. Okay. We have a single lens only now this time. We have the same object with the same height H1, but this time to produce the same deviation angle as it was produced by these two lenses together, okay, how much of focal length it should have? Let me call that equivalent focal length as F equivalent. Again, I can say then tan of delta equal to opposite side as H1, adjacent side as F equivalent. So the tan of delta equal to delta itself. So in the place of delta I can replace this. If I do that, I'll be having like 1 by F1 plus H1 by F1 by H2 by F2 equal to H1 by F equivalent. I got an expression like this, but I know the relationship. What is that? If you consider this triangle, we call this point as a P. If you consider this triangle, I can say that P of O1 divided by, let me consider this point as a R. It's a R, it's a P. So this height is PO1, which is equal to H1. Similarly, this height is RO2, which is equal to H2. I can very clearly define then, if you consider this triangle, I can very clearly write PO1 by PO2, sorry, RO2 is equal to F1O1 divided by F2 F1. F2 F1, sorry. See, sorry, if you consider the whole triangle like this, so you can see very clearly PO1 ratio, PO1 by RO2, that ratio should be equal to what? O1 F1 to O2 F2, O2 F1, sorry. So I got a relationship like this. PO1 by RO2 equal to O1 F1 divided by O2 F1. It is nothing but H1 by H2 equal to O1 F1 is nothing but O1 F1 is nothing but F1 itself. Say F1, O2 F1, O2 is located here and F1 is located here. So O2 F1 is nothing but F1 minus D. F1 minus D is equal to O2 F1. So F1 minus D. So I can able to rearrange this into this following form. So H2 by H1 equal to F1 minus D by F1. So H2 equal to F1 minus D by F1 into H1. I can substitute this H2 over here. If I do that, I'll be having like a H1 by F1 plus H2 can be replaced with F1 minus D by F1 into H1 equal to H1 by F equivalent. On simplifying this, okay. So this equation can be rewritten into the following form as well. So here I can take the H1 as a common factor, I can cancel off them. So 1 by F1 equal to 1 by F1 plus F1 minus D by F1 F2 equal to 1 by F equivalent. So this equation can be rearranged into this following form also. 1 by F1, this parameter can be broken into this following form. 1 by F2 minus D by F1 F2. So this is how we got the formula for the lens, for the lenses which are placed in adjacent manner but not in direct contact but with some little separation gap D. So it's a F equivalent formula. Similarly we can rewrite the same formula in terms of power also. So P equivalent equal to P1 plus P2 minus P1 P2 D. It's the formula we got. So thank you all for listening patiently. So with this wind up, in the next class we can see. Thank you.